Okay, good morning, everyone. Still before noon. My name is Andreas Hildebrand. I'm working as a Ravenna and AOIP evangelist for LABO out of Germany. And we'll covering a bit about the interoperability, the commonalities, and the challenges we have with the IPMX as it's been specified right now, and the well-known and long-standing standards AES67 and 2110. So I will give a very, very brief recap on AES67 2110 just to get everyone onto the same page. Introduction to IPMX. I'll skip probably over that because you have seen that in the presentations before. And then I'll jump into the timing models of IPMX to explain where the challenges are actually buried. And then we summarize up what does that mean for interoperability with a large AES67 2110 ecosystem, most used in broadcast, and the proposed IPMX technology for Pro AV. So let's jump in. AES67. AES67 is an interoperability standard. As you know, the idea was that there were several solutions already out there, like Livewire, Ravenna, Wheatnet, Dante. They were not talking to each other based on IP. And so something had to happen, and that's why AES67 has basically been defined by an AES workgroup over the course of 3 years. And AES67 actually sets forth a interoperability specification, which, if is supported by all these different solutions, would allow an IP-based interoperability among these different solutions without having to go back to the audio layer. And for our topic today, the most important parts are the synchronization and clocking topics. And I'm not going to explain the rest of AES67 because you have heard that many, many times before. And if you're curious, of course, you can go to the AES standards page and download the standard and read all about it yourself. Then I've seen the animations are actually missing from here. Hope this works out well regardless of that. 2110 then came up 3 years later, published in 2017, and 2110 basically is just the same as AES67, but includes video. So it's based on the very same principles, but adds video to the flavor, and its main target application is the professional production environment typically seen in broadcast applications. SEMTI 2110 is not just one document, it's a suite of documents covering various aspects of this technology. And again, as just like with AES67, we are focusing here on the system timing, synchronization, and the audio parts to explain further what challenges we might face. Of course, if you're interested in learning more about 2110, just turn to the webpage and download the standard or visit the FAQs, which give you a nice introduction on that. Well, then for full working systems, there is more than just the synchronization and transport interoperability among systems. You need something which adds to the transport, the functional layers on top of that. And that's where the AMBA NMOS open network media open specifications kick in. They actually are a set of specifications which complement the transport layer. So you have to think like we have SEMTI or AES67 on the bottom, and then we need further functionality specifications like what is available on the network, how can I connect streams together, how can I route signals in devices, and many, many more things. So if you're curious about the AMBA NMOS specifications, here's just an excerpt of those. So there are many, many, many specifications and best practices. And you can learn all about the NMOS specifications on the AMBA or NMOS website. So these are all ingredients which basically are required also, or where IPMX actually builds on. So I'm not telling you what IPMX is because you have heard that today throughout the various presentations, but just the main or baseline or the guiding idea of IPMX at the end is it should provide simple deployment, only requiring basic networking equipment and knowledge. You probably have heard this debate, 2110 is way too complicated. You know, these high data rates, these complicated PTP stuff and everything. We don't want this. We want to have it simple, being simple to be deployed, and not requiring an IT department to set our network. So that was the guiding thoughts of preparing IPMX for the Pro AV market. So basically, as a visualization, we are building IPMX on the proof grounds of 2110 and AES67 and AMBER NMOS specifications. We need to add further functionalities like, HTTP, CC, edit data, encryption, compressed audio, video, and all these kind of things. And all this goes into the IPMX specifications. So that's what IPMX basically is about. And IPMX technical-wise is being specified by the Video Services Forum workgroups. The technical name is VSF-TR10, and then, as you can see, there are many, many different specifications similar to SMPTE 2110, which build a complete, standards suite, so to say. And then further functionalities needed to be added, which are out of the scope of the work of VSF. So that's where AMBER NMOS kick in, and they set forth specifications to adopt further missing functionalities, like what's about the edit data transport, what about the HTTP encryption, and so on. So that's basically how IPMX is being built, and now into the current topic for today. So IPMX applications basically are there to support a full range of applications, like the professional live production system. So because they include 2110 as the specifications, we think that IPMX is also suitable in certain areas of live production. We have the whole range from large, fully synchronous operated applications all the way down to smaller asynchronous AV systems, which feature are typically based on one-to-one connection between an input and an output system, so camera or display, between a single sender or receiver like an HDMI source being transported across the network and being displayed somewhere else. So basically, IPMX thrives to cover the full range of applications, including parts of a typical 2110 application area. Now, when it comes to synchronization and to clocking, IPMX is designed to run on networks which have PTP, the precision time protocol, as the basis for synchronization, but are also looking at networks which do not have PTP as synchronization source. So basically, what IPMX does, it specifies what to do if PTP is present. It also specifies how to operate when PTP is not present on a network. And consequently, IPMX devices basically need to support both types of operations, with PTP and without PTP available on the network. Andrew just mentioned in the presentation before that we are in the process of defining profiles and sort of sub-profiles or functional specifications for that. And that's the small line under here. It might well be that we end up with a profile where senders are not required, even if PTP is present on a network, to support PTP-related synchronization and timing. That would ease and relax a system design or system operation, also the device implementation for certain IPMX use cases very, very much. So that's the outline. And now let's look into the definition of the various operating modes. So I mentioned the full synchronous operation with the presence of PTP. That is basically exactly the same what is being defined in AES67 and 2110. The second operation mode is we have PTP on the network, but we do not want to have a fully synchronized operation because we just want to have an asynchronous input signal being transported, but being synchronized with the help of PTP available on the network. And for those of you who are a bit more into technology, this is what I tend to call the AVB type of operation, because that's exactly what it is. We have an asynchronous input signal, which is not converted to a synchronous a signal with respect to the whole network timing. It's as asynchronous as it is, it's transported across the network, but with the help of the PTP timing information, it can be fully precisely aligned and regenerated, the time regenerated on any receiving side. So the AVB type of operation The majority of use cases for Pro AV, of course, remains the asynchronous operation. We have any sort of input signals, maybe an HDMI signal with video audio coming from a free-running sender. We want to transport that across the network, and we don't want to see PTP on the network, just regenerate that signal on any receiving point. That probably is the majority of applications for IPMX, so there's no PTP on the network, and we call it the asynchronous operation, basically. To understand this, I just mentioned that IPMX devices need to be compatible with all three modes. That has the constraint that we are not yet at the point where we might want to come up with a profile which only requires asynchronous transport to ease the deployment and the implementation of devices. But to understand what I'm talking about here, let me explain a little bit more about these three different synchronization and timing mode, because that's essential to understand at the end. We have this fully synchronous operation as in Ravenna AES67 2110. That is where the media clock for any input signal is derived from the common reference clock. So all the devices, all the media signals are fully in sync. So that looks like this. We have a typical sender application. We have an input signal, AD converter in case of an analog signal. And from there, we are packetizing the media content into an RTP stream. Now, the A to D converter needs to have a media clock to drive it, right? The media clock is generated by an internal local clock, and that in turn is being disciplined by a reference clock on the network. And that reference clock happens to be synchronized by PTP. So in terms of a digital signal, this is the other side of the screen. The digital signal is on the source side controlled by the media clock being generated from PTP. So any signal on the network is fully synchronous. That's the synchronous operation we had in standard studio environment for years with house clocks or work clocks running around as the reference. So any device which wanted to transport signals across my, transport system needed to be in sync, disciplined by a house clock, work clock, any gen-lock signal, basically. So, as I said, the media clocks are following a master clock. They are getting the master clock timing information very precisely through the precision time protocol. So the slave nodes are the individual devices, and these individual devices now regenerate whatever clock is necessary, be it 48, 44, 96 for video, on their own. But since the clock are precisely synchronized to the master, they all have the same media clock, right? That's the way 2110 works in terms of clocking synchronization. There's another aspect to this. When we have exact timing on a network, the exact same timing within every device, we are able to actually align any individual stream on a network, sample accurately at any desired point in time. So a left and a right channel originating from different senders can be precisely sample accurately aligned on any given receiver, just as a very simple example. So we have a sender, or we have senders generating packets at regular intervals. We have packet jitter, various packets delay on the network. See, there are three receivers which see the incoming packets with different delays due to jitter or, more switches to be traveled across. And then with setting a common link offset with respect to the generation point of time, all these receivers can play back the media signal absolutely sample accurately aligned. That is another goodie we get with the precision time protocol and precise timing on the network. So again, main benefits, drawbacks with that is all media clocks are following a common reference, and so the accurate production of the reference clock and phase accurate alignment is possible. And of course, since all media streams are on the same clock, not just nominally, but really on the same clock, there's no problem with receiving streams from different senders in the same device because they are following the same clock. We have deterministic latency with that and can sample accurate align the streams. And if any asynchronous signal needs to be sample rate converted on the input side before it can go onto the network. However, the drawback certainly is the network has to provide PTP with a certain precision and accuracy. That requires some knowledge to set up and deploy PTP on your network. Second mode of operation is the AVB type of operation. So we have an asynchronous input, but we have PTP on the network to timestamp the asynchronous input so that a receiver can exactly regenerate the media clock of the input system, and it's also possible to align the incoming stream to a certain deterministic playout. So in the drawing we had before, this looks like this. We still have the full drawing of an AES67 or 2110 sender. Now what happens is that we break the connection between the local clock and the media clock. So the media clock is now either free running or following an external input signal. But in order to get the exact knowledge about the media clock, we can now relate any cycle, basically, any start of a cycle, to the exact time, which is still synchronized by PTP on the network. So what happens is that we can build timestamp pairs of a clock cycle with the actual time. So even if we don't have the same clock at every device, we can precisely know at every receiving device when has that particular clock cycle or sample, audio sample I'll get on the receiver being generated. And just by observing, the time distances between the different clock cycles compared to the real-time clock, the receiver follows the PTP as well, right? They can regenerate the incoming clock precisely and very, very exactly. On the digital side of things, of course, that media clock is being driven by the digital source, and they have an RTP stream, and they are asynchronous on the network, follows the same principle. I have timing pairs. Main benefits and drawbacks, I can have individual input clocking, so my devices do not have to follow the synchronized common reference clock in terms of the media clocking, so I can transport 48, 44.1, different 48 free-running devices across the network, and with the help of PTP, I have an exact timing relationship. I have deterministic latency with that, and I can precisely reassemble the input clock on the receiving device. However, since those streams do not run on the same media clock anymore, I'm most likely not able to receive more than one stream on the receiving side in terms of being generated from different receivers, because they're all running now different media clocks. And even if it's nominally 48 kilohertz, I cannot concurrently process a stream which has, let's say, 47.999 and 48.001 without sample rate conversion anymore. So we have a slight drawback with this type of operation, but still having the benefit of precision here. So that, again, just a summary, this is the ABB Milan type way of operating. And then, of course, since we require PTP for that, we still have to deal with a somewhat more complex setup in the network. Okay, the third way of operation is the fully asynchronous operation, where there is no PTP on the network. If we don't have any PTP, we don't have a common reference clock. So basically all the devices are running on their own. In terms of the diagram we had before, there is no reference clock anymore, no PTP in the network. We still have an internal clock. We still have a free running media clock generator. IPMX still requires these RTCP pairs being sent, but they are somewhat meaningless to the receiver because the receiver itself does not have a reference to the, referenced internal clock anymore. So basically it needs to regenerate the media clock of the incoming stream, by observing that stream data, just like a conventional asynchronous RTP connection in the past. And of course, with digital, it's just the same. We have the frequency coming off the digital signal. We have the RTCP time pairs, but they are not very useful. I mean, there are some use cases for these pairs, but basically they don't provide much benefit to regenerating the media clock. So the main benefits and drawbacks, I can transport any input signal with any media clock. It can be reasonably well reassembled by any receiver. Of course, that depends on the quality of the sender and receiver clock circuitry implementation. I don't have any concurrent processing of independent streams. Of course, they are running their own clock now. That means the receiver needs to SRC signals when it wants to play out them in any combined way. And I don't have by no means any deterministic latency because I just don't know from the receiver point of view when has a particular signal been generated, because my internal clock is not aligned anymore with any sender's internal clock. So the timestamps are useless, are worthless, so I can't tell how long a particular packet had been on the network. However, the benefit now is very easy network deployment. Just plug devices in. Don't worry about PTP. Just make sure the RTP packets travel across with some decent quality of service so they did not get lost. But don't worry about PTP deployment at all. So basically, it comes down to 4 use cases. We have PTP and no PTP on the network, and we have synchronous and asynchronous operation. So we have the standard AES67-2110 case. We have PTP and synchronous operation. We have the ABB Milan type of operation where we have PTP but run asynchronous input signals. And we have the no PTP and fully asynchronous operation. Well, and the fourth quadrant missing here is basically no PTP but synchronous operation. I would call it synchronous operation. That's the traditional one when we're running house clock around. All devices have the same reference frequency, but no time. Synchronous operation. So what does it mean for interoperability between pure AES67-2110 devices, which were not aware of IPMX at the time they were built, and new IPMX devices? Well, first of all, AES67 devices always require PTP. AES67 devices don't support any asynchronous operation. So that means interoperability with AES67-2110 devices is strictly limited to this first quadrant. We have a smaller or minor issue with the defined precisions for grandmaster. IPMX has a more relaxed precision requirement or accuracy requirement for grandmasters in the system. This might pose a problem with AES67 devices which expect a tighter accuracy from the PTP side of things. May or may not, and it depends actually on the deployment of the PTP on the network. Then AES devices are aware of RTCP, but RTCP has no function within AES67. So they are not generating RTCP packets, which are required for IPMX, actually. But they tolerate their presence, so they are not being distracted by that. And then AES67 does not have specified any control and management mechanisms. Some manufacturers provide proprietary mechanisms. Others bet on some basic NMOS mechanisms, and there are other control mechanisms like AES70 and others out there. So there is no common upper layer functionality where IPMX is mandating for certain NMOS capabilities. So that, in a minute, we don't have issues with the actual streams, because the stream formats, which, the RTP packets, the stream formats in the RTP packets is identical to what AES67 specifies. So IPMX uses the same mandatory formats for the RTP packets. So we don't have any issue with the RTP stream itself. I know, that's the 4th minute. So, STP information is still required for AES67 and IPMX anyway. So what does that mean for the interoperability? Let's look at an AES67 environment with PTP where I want to add IPMX devices to. How does the interoperability work out? So first of all, the IPMX devices certainly will log to the available PTP on the network. And if an IPMX transmitter or a stream issued by an IPMX transmitter needs to be received by an AES67 receiver, it only will work if that stream is issued by the IPMX sender in full synchronous stream operation mode. So it cannot issue an asynchronous stream on the network. It can do so, but it cannot be received by an AES67 receiver. The other way around is not a problem at all, because IPMX receivers, even if they are not those who tend to work with PTP, can always receive an AES67 RTP stream. It's just ignoring any time information and could work asynchronously. But most of the IPMX receivers will acknowledge the presence of PTP and will offer synchronous, or at least the AVB style asynchronous operation with precise time alignment anyway. So IPMX receiver will always be capable of receiving an AES67 stream. The other way around, we have a 2110 environment. We have an IPMX environment where PTP is present or not, right? And then we want to add AES67 2110 to it. What happens? Okay. AES67 devices can only work if PTP is present. So if PTP is not present, AES67 devices cannot work in that IPMX environment. Then looking at the streams, an AES67 transmitter can always be received again by an IPMX receiver, same case as before. And an IPMX transmitter can only be received by an AES67 receiver if it's operating in full synchronous operation with the PTP being present. So, summing up, interoperability is possible, but only if a common reference clock via PTP is available. Streams to be received by AES67 devices need to be run in full synchronous mode. Stream configuration is something which is, stream configuration is no problem at all, because they have the same requirements, mandatory requirements. And then clocking accuracy needs to be aligned between these devices, and control and management is not part of AES67. So it's upon the manufacturer to actually see if he wants to add something or if NMOS is present or whatsoever. So we probably need other means of configuring AES67 devices to receive IPMX clocking. That's it. Don't think we have time for questions, or maybe we have for one or two, if there are any. Otherwise, I'm around after the presentation. If not, thank you very much for attending, and here are a few more references where you can find further information. Thanks a lot.